So thanks a lot for having me here. I'm very excited to share with you these new ideas we developed with Gia Desali and Florian Kuhnel in Munich. And yeah, so let me just, okay. So the goal of the talk, so there is an issue which, of course, I mean, there is not much we can do about it, but namely that the microscopic structure of black hole remains to be understood, right? And one of the main issues, we want to put it that way, is the lack of probes of its quantum properties. So the idea is to look for microscopic theories or theoretical approaches that potentially can provide us with such macroscopic observables. And if this is possible in certain regime, then it's worth exploring. And okay, today I will try to argue for one such phenomenon that can possibly give such macroscopic observable, and it's related to vorticity in black holes, okay? So this slide is really introductory. So there are two roads with which one can tackle the question. And one of these roads is related to the black hole's quantum and portrait. It's not the road I'm gonna provide today, but okay, it's the road that made us ask first the question. And what is the black hole quantum and portrait? So this was developed by Valley in 2011. And okay, at the time I was still a high schooler, but so not so far, but also not so far, not so much time ago, but also not so close to this, so not so recently. And the idea is the following, namely that there are indications that black holes can be described as condensate of soft graviton of wavelength r and frequency omega 1/r. And in this language, when we try to understand black holes in this language, what happens is that their mass turns out to be equal to the number of constituents, number of gravitons multiplied by their energy, omega and graviton. And okay, they obey a maximal packing condition. It's the way it's called, but it's or also a saturation condition, namely that the gravitational coupling alpha multiplied by the number of graviton is of order 1, okay? And the gravitational coupling, you understand, it's basically the typical, the gravitational coupling evaluated at the energy scales relevant for black holes, so at the radius. So it's basically 1/r squared, the radius of the black hole, in units of Planck units. And if this saturation condition, which can be derived in many ways, but okay, here I'm not gonna talk about this, so just take it. What happens is that the following entropy law is recovered, namely that the entropy is equal to the number of graviton, which is 1/r coupling due to this saturation. And by definition of the gravitational coupling, you recover the Bekenstein area law, okay? And in this language, because we have a sort of, by the way, I want this to be very informal, so feel free to ask questions and interrupt me at any step, no worries. So in this picture, Hawking emission is understood as the scattering of gravitons constituents, okay? And one can understand why semi-classically no other effects are seen other than thermal Hawking emission. And the reason is that the semi-classical limit corresponds to the limit where the gravitational coupling goes to 0, the gravitational number of constituents goes to infinity, while keeping the coupling of the collective coupling finite equal to 1, and the radius finite, okay? And one of the advantages of this approach is that, of course, black holes are very big, but not infinitely big. They don't have infinite many constituents. Therefore, at finite n, there are corrections to the emission, and one can address several issues that there are related to page time, understanding better page time, and so on. But the main point that is relevant for us today, and that's the point that started the quest for this research, is that in this picture, the black hole is made of condensate, and condensate, we know, normally if you rotate them at a certain point after a critical angular frequency, they start rotating, they start displaying vorticity. So the natural question we asked was, what about rotating black holes? So
can I ask a question, actually, on the previous page? So is this meant to be a heuristic model, or is it a precise thing in which you can do concrete calculations and get numbers that are then reliable?
Are you asking whether there is a limit where I can recover a strict Schwarzschild metric, or if there are properties of black?
So first, there's a bunch of standard properties, right, for like classical geometry properties of black holes. That's the first thing. But then there are also some situations in which people actually have some understanding of the black hole entropy, like in certain highly supersymmetric situations. There's an old calculation by Strominger and others.
Yeah, so
they actually calculate the entropy. So if you have a proposal for what black holes really are, then it should recover this if it's really like very precise.
So so what I can tell you is that the answer to your question, I think, is somewhat in the middle, namely in the following sense. So entropy in this system can be understood in the following way, namely as microstate degeneracy due to fluctuation on top of the condensate. And this is what recovers the notion of large entropy. In this framework, you can understand Hawking emission, for example. Of course, the geometry you cannot recover. By the way, there is an exact calculation in string theory made out of this large n graviton construction. And this is a work by Dvali, Lust, and some other people. And I can give it to you if you're interested, where they show some of these property emergence and fully calculating. Yes.
And along the way, there's some understanding of why the entropy has an area law instead of a volume law for black holes.
Yeah, I have a comment on that in a few slides, and
I'll wait. Yeah. I'll wait. Okay.
So it turns out that here now I will tell you today about a different approach, which is somewhat parallel to black hole to the one I just showed you, but it's important for understanding black holes. Okay. And this is an approach which is rather more recent. And this is also was asked by Dvali like 2 years ago when I was starting my PhD. And the question is whether known properties of black holes are unique to gravity. So for example, there is this example that Dvali always likes to make, namely if I have a bucket of water and I see it evaporating. Of course, I know why the water is evaporating because I have a microscopic understanding of it. But if I were not to have such a description, what I would do is look in other systems and try to look for, I would take other buckets of other liquids and look for sort of universal properties shared across this other system. And okay, maybe this question should have asked 50 years ago, namely look for other system with the same properties, but it was not done. So okay, this is what was started by Dvali in 2019. And this is how I would sum up the whole research program if I were to put it in one slide. So it turns out that there is a guiding principle that is unitarity. And what Dvali, basically I will try to comment in the rest of the talk, give you the necessary literature and hints to understand this first part of the plot and then focus on maximal spin. But okay, what it turns out is that there is a guiding principle that constrains what is the maximal entropy that a localized system can bring, and this is area law. And simply by requiring this area law, this area law scaling turns out to be the culprit for all other properties, for example, these ones that we observe in a black hole. Okay, I'm gonna try to make this more precise, but for example, one of the consequences is Hawking temperature emission, T temperature approximately 1/r, a page time information retrieval, maximal spin. I will also briefly comment on the notion of sort of notion of horizon that emerged from this requirement. Okay, so what is it about? So this is the series of archive. By the way, these articles are published, so okay, but the archive are for reference. So what was shown, and this was shown from many points of view, is that given a self-sustained object of size r, this could be in gravity, but also in whatever renormalisable theory, doesn't matter. There is a maximal the entropy is maximally bounded from above, and I will give you an example of such system later. And the maximal bound is in terms of area in units of the Goldstone coupling constant. So this you can rewrite as Goldstone coupling constant equal inverse decay constant. And what are these Goldstone coupling constants? These Goldstone coupling constants are associated to the symmetries broken by the localized configuration. Okay, Namely, there are Goldstone associated to this configuration that are gapless. These Goldstone, and these are the Goldstone that provide the large states, the large microstate degeneracy, forming the entropy. And it turns out that if you don't want, unless you don't want to violate unitarity, the entropy can be almost proportional to area. Okay, and these are the literature if you're interested. Okay. So
what's a concrete example of a symmetry that you're saying is broken here?
So there are two, for example, in the example I'm gonna give you, I'm not gonna discuss this explicitly, but in the example I'm gonna give you, there is really two symmetries. The one symmetry that provides Goldstone is internal in terms of field theory, because in terms of field theory, it's gonna be in internal space. The other symmetry, which is there in every system and is specific to black hole, would be Poincare symmetry. And the main point is that the Goldstone coupling of the theory would be G Newton, but I'm gonna comment on this in a few moments.
Thank you.
So for example, objects saturating the above bound, they are called saturons. This is just not to repeat every time that we consider object that saturates this bound. And for example, black holes are an example of saturons, okay? For example, in that case, the Goldstone decay constant is the Newton constant. So, but the main point is that saturon configuration can be found also not in gravity. And an example of these are condensates. But okay, I'm gonna focus today in, by the way, this condensate part is something I want to work in detail better in the future. But for today, we'll focus on an example which is provided in renormalisable QFT, okay? And the main message I want to take home, one of the messages, is that after all, black holes are not so unique in their properties, okay? Okay, they have many unique properties, but the ones I listed before are not so unique.
Sorry, could I ask a question here as well?
Sure.
But then if you're looking for, one of the features of gravity has a universal coupling, so nothing can escape. So
yes,
if you now go find saturons, some things can escape and some things don't, right? Depending on what it couples to.
This is an excellent question. Yes, thank you. So I'm gonna comment on in a bit about this specific point. And the short, but maybe it's easier if I first give the example of Saturn, so I can tell you how it differs from gravity in this sense.
Yeah.
Okay.
Yeah, because then I would say it's not a black hole. You see, if something can escape.
I'm just saying there are some properties observed in black holes that
I
can
see.
also in other systems.
I
okay.
See. Okay.
This is
yeah.
the idea. I'm not providing any microscopic picture. I'm not on the side of the first slide where I was giving a portrait of black holes. What I'm saying is I'm looking for other systems that display similar features. Okay,
but
this
not,
is the first point.
But not all features. You just want some features. I
see.
Okay.
Some key features, yeah, that I'm.
Oh, okay, thanks. Yeah, okay, that's fine. Thanks.
Okay, just to be clear, how this property follows has not been originally my research. This has been done by Dvali and also other people in my group, specifically these 2 points. But what I find exciting about my research is that looking into the maximal spin, we found reasons to understand the maximal spin bound that we observe from black hole, or at least indication of why that it is the case. And we also came up with region of the parameters where we can have macroscopic prediction, therefore maybe testing the whole picture. Okay. So let me give you an example of what is a saturon in a renormalisable field theory, okay? So let me consider the following theory of a scalar field in the adjoint representation of SUN. Other representation can work as well. I focus on SUN and the adjoint for simplicity. So this is like an n times n matrix in flavor space, right? Which is traceless and Hermitian. And okay, the Lagrangian I consider is the following. There are 2 parameters that are important other than the flavor dimension, the dimension of the flavor group. One is the coupling, which parameterizes the 4-point interaction, the microscopic interaction of the theory. And then there is a physical scale, which I denote by F, okay? And okay, unitarity, what it does is that it puts a bound on the collective coupling. You see, there is a collective coupling, which is given by it's basically a coupling of the model, because we have n flavor. And this collective coupling is alpha n. And this alpha n by unitarity should be somewhat smaller or approximately equal than 1, okay? That means that we can work in, first of all, there are a few remarkable things about this model. The first remarkable thing is that the model is renormalisable. One might think that some of the gravity's properties are special to gravity because of its non-renormalizability. So a renormalisable model was proposed. The other thing is that we can work in a double scaling limit, namely this microscopic coupling can be made arbitrarily weak, and we can take the large n limit while keeping the combination alpha n finite, a sort of, this is like a sort of, this is basically Toft coupling, right? Okay. So you see the potential here is quadratic, therefore it's bounded from below, therefore minimizing the potential corresponds basically to look at zeros of the potential. And it turns out that there are many degenerate vacua in this theory. So there is a symmetric vacuum, which is for phi equal, expectation value of phi equals 0. And in this sector, the theory has a mass gap, okay? And one can also have many other vacua, they're all degenerate, but okay, there is a SUN minus 1 cross U1 vacuum, which is the one I'm gonna be interested in. And there are also SUN minus 2, 3, 4, many other vacua. But okay, the order parameter for this vacuum corresponds to the following diagonal choice of the adjoint, where you can see it makes no distinction among n-1 subsector of the flavor space. And what it turns out is that we are working now in large n, okay? I'm assuming that n is very large. So in this limit, okay, there is a normalization factor, but in this limit, what happens is that there are 2n gapless modes, okay? So this is sort of the broken phase of the theory. Let me then call it like that. So the idea is to build a bubble. So the way we build a bubble is that we imagine that there is a bubble in the SUN minus 1 phase, the broken phase inside, and this will provide 2n massless modes. Okay, there are 2n massless modes. These are the Goldstones of this broken with this order parameter. While outside the bubble is surrounded by SUN, so it's the theory has a mass gap. Okay. So what we can do is we can make a field ansatz. We can choose phi to be equal to the expectation value of the field to the order parameter in the SUN minus 1 vacuum. And then we can look at the profile of the resulting bubble. The main point is the following, that you see that the bubble is highly degenerate in the sense that it has, it has 2n massless modes in which I can store information. These are the Goldstones associated to this in the interior. But outside, this Goldstone, these degrees of freedom would be massive, so there would be a gap. So you see, what can happen is that I can store information inside of the bubble, but because here this information is basically energy as an energy cost which is 0, it's gonna be difficult for the bubble to get rid of it, because outside these occupied modes would have a gap, so it would cost energy to produce them. Moreover, you should notice the following: all the vacua were degenerate, so this bubble is unstable. So we can do two things at once. We can excite Goldstone modes in the interior of the bubble, so we can add information, and the product result of this process will be that we will also stationarize this bubble. Okay, so you see what we can do. We can take the original ansatz for phi, perform a transformation, and this transformation will mix. It's a standard. It's similar to the standard construction you would do for non-topological solitons. We basically mix a broken generator in the direction of time with some frequency omega. T hat here is one broken generator associated to the Goldstone in the interior of the bubble, okay? And okay, this is basically the same construction as for cuboids, just generalized to this large n theory with the adjoint representation, okay? So what happens here is that we added information in the interior of the bubble, and this stationarizes the bubble, okay? So okay, this is just how the equations of motion gets corrected when we add this omega transformation, and now we can solve for this system. We can solve this equation of motion, and what turns out is okay, there are some quantities that I think are relevant. The first quantity is that associated to the transformation I performed in the broken direction in terms of time, there is an associated charge, which corresponds to the number of Goldstone I'm endowing the bubble with. And okay, this is just a quantity, but you should remember that there is this feature, and it depends as 1 over alpha, the microscopic coupling, and then some combination of m omega. The radius is also found, a stationary bubble that solves this equation. The radius is found. Basically, this equation corresponds to solving for the bubble in inverse potential, right? So the radius of the configuration has the following nice scaling, and the energy goes as omega, the frequency of this of the Goldstone, multiplied by the number of Goldstone. The number of states is computed in the following way. So one can ask how many degenerate patterns there are in this answer, in the information I'm providing to the bubble. So I define this microstate degeneracy. I count it in the following way. So each choice of occupation number in the Goldstone corresponds to a pattern that I denote in this way. So at each broken generator, they are 2n. I associate an occupation number, and 1 and 2, so forth. And the total sum of these occupation numbers should be equal to the number of Goldstones. This then, with Stirling, I can compute what is the number of degenerate states that the configuration has. And then I use this number of states to estimate the amount of entropy of the configuration. Okay, so this is the most simple way you can define the entropy for a given configuration, namely counting the amount of microstate degeneracy that your model has. Okay, so what happens is the following, and basically the configuration saturates unitarity bound, namely it becomes a saturon when these relations are imposed in the parameter space of the theory. First of all, the frequency should become of order of the mass of the quanta, and this should be of order 1 over radius, the size of the bubble that we are considering. Moreover, the number of Goldstone, the charge that I use to information I input inside the bubble, should be of order of the flavor size of the group n, and this should also be equal to 1 over alpha. I remind you, alpha n equal 1 is the maximal bound from saturation or from unitarity that one can get. Under this assumption, you see what we are doing is basically the following. We have a saturation of unitarity in terms of collective coupling, alpha n, and this is a coupling associated to the theory at n, but there is also a saturation of unitarity in terms of the state we are considering, because alpha multiplying by a number of Goldstone, that's a property of the state we are considering. And this could always, so this also needs to obey unitarity bound. So for example, when we think in some background, I mean, when we build a generic state, the microscopic coupling of the theory combined with some macroscopic exploitation value of the field will give us some notion of collective coupling. This is that coupling. And the other thing that we are looking at here on this side is basically we have only one scale that matters for the theory, one physical scale, which is the size of the black hole, the size of the bubble. So what happens is that if this is realized, and the details are in the volume, I'm happy to discuss them maybe at the end because I want to rush to vorticity. What happens is that the entropy of the configuration displays an area law precisely in units of G Goldstone, which is also equal to the flavor size of the group, which is 1 over alpha, and the energy of the bubble becomes equal to the number of constituents multiplied by their energy, their soft energy, their frequencies, which is 1 over r. And you can see that in this framework, there is an analogy with black hole from the point of view of the area alone. Here, I'm not saying anything about the other properties, but if there is a correspondence between G Goldstone and G Newton, which is related basically to the typical scale of the theory F with M Planck. Okay. So in this series of work, the saturated bubble is shown to have also a thermal spectrum and the notion of information horizon. Let me tell you what we mean by what they showed in these works. I can tell you. So this is related to the fact that black holes have an horizon basically for everything. But this bubble does not, of course. It's not a gravitational black hole. The type of horizon that this bubble has is an horizon in terms of flavor space, okay? What happens is that if you try to to perturb the bubble in the flavor that with some flavor. You couple some flavor field to flavor non-trivial field to the adjoint, and you try to perturb the bubble. What you will see is that basically the bubble will maintain its sort of horizon, its profile will stay there, and basically it will not let escape any of the information. Okay, so this is a sort of information horizon in terms of the flavor structure. Okay, this is the best we could get. Okay, so let me comment again. So you see, what we have is that with unitarity, and unitarity saturation imposes the collective coupling of the theory, the Toft coupling, to be of order 1. If this is satisfied, what happens is that we recover an area law scaling for the entropy. And from this, you understand there is a notion of working temperature. Why? This notion of working temperature can be understood as bubble rescatterings of the bubble constituents. So we have a bubble. This bubble, of course, is not eigenstate of Hamiltonian. It cannot be eternally stationary. There are quantum fluctuation on top of it. And this leads to rescatterings. And the main point is that, you see, in the limit where the bubble is a saturon, there is only one scale in the theory. And the coupling, the collective coupling that would be responsible for a decay is of order 1. Therefore, it's not hard to realize that the decay rate of two constituents of the bubble in two outgoing quanta is proportional to 1 over r. Okay, it can only be given by this size because it's the only physical size in the system. But okay, there are computations. I'm just providing qualitative argument. Moreover, you can understand why there is a notion of sort of thermal-like spectrum. Because if we were to consider the emission of highly energetic quanta, so the bubble has a lot of quanta of energy 1 over radius, that's the frequency. Therefore, to produce highly energetic quanta, we need to rescatter multiple constituents. So if we look at the decay rate of delta n constituents, much more than 1. So if we look at the scattering of many constituents inside the bubble into two highly energetic outgoing quanta, what we get is that we will see that there is an exponential suppression, okay? This is like a Boltzmann suppression. Therefore, it provides an effective sort of thermal spectrum to the theory, to the saturon. There is also an understanding of what is page time in this saturon, renormalisable saturon picture. And namely is the following. Of course, the initial state we consider is pure. And therefore, it cannot provide a purely thermal spectrum because it's a pure state. And this is solved because, of course, the theory has also fluctuation, and in particular, this seemingly exact thermal spectrum has 1 over n deviations. So that means that it's corrected by 1 over n deviation. And the typical scale of these deviations, where they become relevant, is exactly given by the time scale of typical emission of one quanta, so radius, multiplied by n, because that's basically the 1 over n is basically the microscopic coupling of the theory. It's like going higher order in the effects. So you see, this effect would not be there in the infinite n limit. There would be no, this time would be infinite, and information from the bubble would never be restored. This is the time scale that corresponds to the retrieval of the information stored in the Goldstones, so the internal information of the bubble. Okay. So okay. Here I just give heuristic arguments, but I hope I manage at least to partially convince you of the whole program, at least to give you a hint of what it is about. And I want to—
Can I ask a question here at this point? So your theory is always unitary, but you're imposing perturbative unitarity constraints here, right? So how do I know that that the theory is just always strongly coupled, and I'm just in a different phase and I never see any of this behavior?
Yeah, so thanks. Yeah, that's a good question. So you see, the point is that the way we impose a bound of perturbative unitarity, namely the collective coupling, should be order 1. That's correct. Now, whenever we go in a region where this unitarity is violated, what happens is that the theory becomes strongly coupled, and normally what it requires is the need of a new language.
Right.
That's what we learn everywhere in field theory.
Exactly.
So here, this is not necessary. We are just working in the limit where this is still perturbatively under control, and when we are saturating entropy. Okay.
I see. So you're speculating that this is the description, the perturbative. There's a perturbative description, and the strongly coupled description doesn't exist.
Okay, but look, this is motivated by the following. When we look, for example, in this M portrait I was telling you about, this, okay, here we are working in the regime where n is very big and alpha is very small.
Mm-hmm.
And also in that portrait, microscopic sort of resolution, what is seen is that we work at the boundary where close to saturation of perturbative unitarity. Mm-hmm. Beyond that, if we go beyond that, what happens is that the theory becomes strongly coupled, and we need a totally other description. But for black holes, we are always in the regime where this description is working. So it's
But would this behavior survive if you went to strong coupling? It probably wouldn't, right? Or you don't know, right? I guess
I don't even know what it means. I don't even know what it means to go into strong coupling, because when we go to strong coupling, what happens is that our language is no longer valid.
Exactly. Yeah.
It means that we should rework our theory in a different degree of freedom.
Yeah, exactly. The degrees of freedom change. Okay, thanks. Yeah.
So now let's look at this maximal spin. So we are looking at this bubble like saturon, and we know of a way to spin it. At least as far as we know, there is one way which preserves axial symmetry, and this way is vorticity. Okay. So the way we do that is that we take the previous ansatz for the field, but now we allow for a further mixing. Before, the mixing was just in the temporal direction. Now we also allow some Goldstone's mixing in the direction of the polar angle, okay? So phi is the polar angle of the configuration, kappa denotes the winding number. And basically what happens is that this induces a term that forces you to have a vanishing profile in zero. So you can think of this, therefore, of this profile as a sort of something like this, okay? It's a bit more complicated. It's not so spherical with this hole in the middle, but okay. That's basically the qualitative picture we have in mind. And here I'm showing you numerically that some solution exists, okay? Some solution of vortex. So the theory starts at 0 in the center, and then it reaches the value of the bubble, and then it decays outside of the boundary. Okay, this is just for arbitrary values of parameter space. I'm not specifically at saturation. I'm just looking at whether a vortices solution exists in this theory. Okay, so it turns out that if you compute the angular momentum of the theory, this is just done looking at the energy momentum tensor of the theory in the 0 phi direction. What happens is that the angular momentum of this configuration under these ansatz is given by winding number multiplied by the number of Goldstone that we input to stationarize the bubble. So this is also like the charge of the theory. And it should be noted that, okay, for simplicity here, we chose to use the same broken generator as for the time transformation. One could do generalized to other transformation that's not relevant. A nice feature, however, is that there is a multiplicity of broken generators. You see, there are 2n of such generations, so this bubble is realized in this multiplicity. So there are multiple directions in the broken phase where this bubble can be realized. So this is very similar also here. This is just generalized to this adjoint field, but there were previous studies in U1 where this type of construction were done for cue balls. For example, these are the people. And I think there was also some earlier work where these are the people that worked out the full solution in 3 dimensions, but there was some earlier work making estimates and presuming that this configuration exists in cue balls. Okay.
Is there anything being varied between the 3 curves that you show, just the parameter omega, or are other parameters varying as well?
Oh, yeah, exactly. That's why I'm saying that I'm not necessarily exploring saturation. Here I'm just varying omega, fixing basically F and alpha to 1. So you remember that here I had this property that the radius of the configuration goes as 1 over omega squared. Okay, this M is fixed. And so you can see that basically as I decrease omega, you get bigger and bigger type of configurations.
I see. You can make a bigger and bigger bubble with a core size for like a vortex in the bubble, which is fixed by decreasing omega. Is that right?
Yeah, that's basically that's exactly the point. Here, the mass, I kept it fixed. That fixes uniquely the size of the core. Okay. It's not at saturation in this sense. Okay.
I see. Very good. Thank you.
So you see what is happening now. So this is the angular momentum that you obtain. But when we look at saturated bubble, this angular momentum is going to be equal to also the large n, the big N, the flavor size of the group. And this is also equal to the entropy. Therefore, there is a constraint, namely that the vortex energy should be smaller than the bubble energy. Okay. So because we want to preserve our bubble, this basically corresponds to requiring that saturation is preserved even in presence of vortex structure. Okay, so namely by imposing that the spinning, the rotational energy is smaller than the bubble energy, we obtain that kappa, the winding number, is of order 1. Here we are dropping numerical coefficient, it's of order 1. Maybe it's a bit bigger than 1, but surely it cannot be much bigger than 1. And the reason for that is that if it was much bigger than 1, what would happen is that saturation would be lost, and we would lose all the nice property about the area scaling and all such properties. Okay. So now what happens is the following. Therefore, there is a maximal value of winding number, and now there is these striking similarities, namely that if I look at the bubble at saturation, I have that the maximal spin is m squared multiplied by the Goldstone coupling associated to the theory. And this is strikingly similar, again, under correspondence of G Newton going to G Goldstone, to the maximal spin of black holes, okay? So we have a lot of striking similarities. So suppose that we didn't know what black holes are and we just looked at gravitational saturon. What we would observe is an area law upon saturation, and this is checked. Thermal spectrum, which is checked for black holes. A partial notion of information horizon, which, okay, as we discussed, it's not exactly checked for black holes, but in some sense, it's very similar. A notion of page time, which is the time after which I start retrieving information about the interior of the bubble. This also checks. And also maximal spin bound. So the natural question that we asked is whether vorticity is there for black holes. So notice the following. All these points are facts. I just looked at saturated bubbles, and it turns out that they, just from a requirement of entropy, of saturation of perturbative unitarity, I recover a lot of interesting properties that I observe in black holes, which therefore are not so mysterious. But now I want to make a statement. This is a conjecture, okay? And here, this is the key point I want you to, here we can stop and discuss if you wish. But the conjecture is the following, namely that highly rotating black holes corresponds to graviton-condensate endowed with vorticity, okay? So this is, as I told you, this is motivated, for example, by the black hole and portrait, because there indeed they are condensate, the black holes are graviton-condensate, and if they are rotating, we expect them to have vorticity. There are some nice features, namely that the degeneracy of Goldstone vacuum, responsible for the maximal entropy, is also the one responsible for degeneracy in the vortex configuration, namely that the generators, the direction, I have 2n direction in which I can realize the vortex, and this can give for some stabilizing property to the vortex. What is the outcome? For example, this conjecture would give a rationale for the maximal spin bound of black holes, first of all. Also, an interesting comment is that there can exist non-stationary, non-axisymmetric configuration with zero net vorticity, but multiple vortices, sort of like the picture I showed you at the beginning. And this maybe can help us understand slowly rotating black holes or something like that. But the bigger point is that there are phenomenological consequences that stems from this conjecture, okay? And this motivates why this conjecture is made, because there are consequences that can be used to check it. But of course, it can be that the following is true, that the conjecture simply doesn't hold, and that black holes are very special objects. Gravity does something special about it. So the first possibility is simply that black holes do not support vorticity, although we know that there are solutions of black holes pierced by vortices, and those exist. The second possibility is the following, namely that the maximal spin of black hole is there because for a black hole that is rotating more than that, it would necessarily need to display vorticity. And therefore, it's the way of black hole to forbidding the appearance of vorticity, okay? This also would be a nice theoretical understanding of why there is the maximal spin bound. And then the phenomenological consequences I'm about to tell you do not follow there. But okay, let's look what they are. And this is why it's motivated. The construction is motivated. Yes, I see there is a question.
Can I ask a question as well? Again, sorry. So I'm a little bit confused. In the saturon discussion, there's a standard quantum field theory with a standard global symmetry, which is continuous. It is spontaneously broken in some region, and as a consequence, you have Goldstone bosons and various other nice things. I don't understand to what extent any of this is supposed to be true for gravity. Gravity has no global symmetries anyway. I don't understand which global symmetry. Gravity has no global symmetries. There are famous things about this, right? Not only that, but even if you ignore the alleged constraints on quantum gravity, I don't understand which global symmetry is supposed to be broken in the black hole interior. It cannot be Poincare because Poincare is gauged anyway. It's not a global symmetry in GR.
So the point is the following.
What is going on?
So let me go step by step to address your question. Okay. So the first point is that in the condensate picture of this, where this black hole is described in terms of marginally bounded gravitons, as a condensate of marginally grounded gravitons, there are Goldstones, there are gapless modes that are associated to the fluctuations on top of the black holes. These are the Goldstone bosons associated to the broken Poincare symmetry in that picture. And you can understand this in the following way. There is of course, okay, as you said, the gravitational field can be gauged, but so what? You can still define it. And what happens is that if you look from the point of view of an asymptotic observer getting close to the black hole, what happens is that this gravitational field acts as the order parameter that is effectively breaking the Poincare. And you can understand why the Goldstone collective coupling is M Planck. The reason for that is that this order parameter becomes maximally end of order M Planck precisely when it reaches the horizon of the black hole. Okay. So basically, the Goldstone associated to Poincare symmetries are the ones responsible for the black hole microstate degeneracy. This is what we see in the condensate microscopic picture. Okay.
I see.
This would be the answer. Then, of course, at the level of macroscopic gravity, these Goldstones are not observed because that is in the limit of large n. You do semi-classical configuration, and you do semi-classical computation, and you take the limit of infinite on infinite n when studying black holes. So, strictly speaking, there is this point which is a caveat in the whole argument. Okay, that serves as a caveat. But okay, you understand.
Okay. Thank you. Please go ahead. Yeah.
Okay. So let me then tell you what are the consequences of this phenomenon. So this is what I'm about to tell you is a phenomenon firstly derived by Valens and Janovic, and then Sherman and other people here generalize this for a generic effective field theory. Namely, the statement is the following. Whenever I have a global vortex which is interacting with charge matter under arbitrary U1 gauge, what happens is that there is automatically a trap associated to the magnetic field. So that means that if you have a global vortex and some charged matter around it, what happens is that the vortex will be magnetically charged. And okay, you can understand this in this. This is just a calculation of how you could do that. You can denote by chi plus, chi minus the two charge field, and psi the order parameter of the vortex. This is the interaction term that you get in your effective Hamiltonian. And you have an asymptotic, given the vortex, you have an asymptotic condition that the gauge field needs to satisfy. Okay. This is the asymptotic condition, and you can integrate this asymptotic field to obtain the flux, the magnetic flux. And it turns out that basically this magnetic flux is 1 over charge of the particles around the hole. And then there are some winding numbers. Kappa is the winding number of the vortex. Kappa plus, kappa minus are the integrated winding of the positively and negatively charged particles. And you can see what are the source of this flux. There are different sources. So for example, one possible source could be if I have some neutral plasma around the black hole, but made of charge components. This could be a source for this flux. The other source, for example, could be charged dark matter. Okay, the only requirement is that really we need some mobile charges, okay, that do the job. Then the plasma surrounding the hole can be neutral or can be charged, doesn't matter. Moreover, what we see is also the following. You see that the fractional flux, the flux is fractional. You can see this quantity is clearly fractional. And what it means is that this can further stabilize the vortex due to this fractionality of the magnetic field, which is hard to get rid of for the black hole, okay? So what is happening is the following, that if U1 gauge, in our case is U1 electromagnetic, which we expect gravity to couple to electromagnetism, there is a natural support for magnetic field given the presence of an accretion disk, for example, which is the form of some neutral plasma, or some charged dark matter, for example, okay? So you have to have in mind this picture that there is a black hole which is naturally pierced by magnetic field, okay, according to this picture, okay?
Right, you're in the Higgs phase, right?
Yeah. So effectively, you see, thanks, this is an excellent question. Effectively, what is the role of this charged component, neutral plasma or charged dark matter, is to give a locally a mass for the photon, right? You can show that if you have charged dark matter, effectively it realizes the Higgs phase for the photon. So this is what is going on. So whatever does that is enough to realize this trapping. So okay, here this is just, okay, this is my terrible drawing skills. This is just to tell you about BZ emission. So there is this phenomenon that whenever there is a black hole endowed with a magnetosphere, if it's highly rotating, it can emit powerful jets. Okay, so namely, it goes in the following way. Imagine that you have some magnetic field, some magnetosphere from the black hole. Some magnetic line will manage to close themselves on the hole, but others, so for example, you see this line. Eventually, what is happening is the following: that there is some space-time dragging due to the rotation of the black hole. And eventually the magnetic field, as it goes away from the black hole, it can no longer keep up with the rotation, and this necessarily opens, okay? And this leads to the production of it. This because basically to keep following the rotation of the black hole as it goes far, it would have to go faster and faster. Eventually it cannot keep up with the black hole rotation. And okay, this is how they estimate the flux, the resulting emission. And okay, classically, of course, we know that black hole cannot have magnetic field, and it's unclear, for example, what is the mechanism providing such magnetic field on the black hole. Although these type of jets are observed, for example, in M87. So the standard approach is the following: people, at least people that do simulation of AGN, like active galactic nuclei, such as this shadow of the black hole that we observe. They observe very powerful jets, and they can be motivated only if there is something like a BZ type of emission. The way you justify the presence of magnetic field on a black hole is that there is infalling matter, and there is this accretion disk that needs to be specifically magnetized, okay? And as the matter falls, because of the magnetization of this disk, what happens is that it can continuously source and attach temporarily a magnetic field on the black hole, therefore leading to this type of emissions. Now, I'm not phenomenologically strong enough to tell you whether there are some problems with mechanisms, some things that are not understood. For example, as far as I see, it's not clear exactly how these magnetic field in the disk, which are normally slippery, they tend to reattach. They need to be coherent on very long scale, comparable to black holes, while magnetic field in this type of plasma tends to be slippery. Maybe the origin of them seems to be an open question, but it doesn't matter. What I'm saying is that there is also another possible source, which could be due to the vorticity. Namely, we can have some magnetic field naturally supported by black hole. And this can lead to the emission of jets, okay, in general. So let's just, for honesty, I will give you some numbers. So what is the main message is that the jet emission can take place even without the need of creating magnetized disk. That means that I can observe a black hole. There is no accretized magnetic field around it. Maybe there is just a rotating black hole. And I observe some jets or some magnetic field associated to it. This would provide a smoking gun for the scenario. Let me give you some numbers just to get a rough idea of what we are needing. So for example, you see, this kappa was the winding number of the vortex, which would need to be of order 1. Then the other there is this kappa plus, which is the positive winding of the positively charged particle. This quantity, for example, we can assume in the picture, in the axial symmetric solution I just showed you, that this is of order 1. Of course, if I have multiple vortex structure, I can have this following situation. Look. You see, this is the constraint on the 2 kappas. So this is of order 1, and I expect also these ones to be of order 1. I could have a very different picture when, for example, the total net vorticity of the black hole is of order 1, but these net vorticity are canceling each other and they are very different. So I can think of a black hole where basically I have a lot of vortices and anti-vortices, but the net vorticity is of order 1. There would be a question for how the stability of this vortex configuration takes place, which we haven't tackled yet, but that's also a way to boost the flux. Another way to boost the flux, assuming that these kappas, these winding numbers are of order 1, is that the charge of the resulting particles is very small. So for example, if we wanted to match the jet observed in the active galactic nuclei of M87, what we would need is a millicharged dark matter with a charge of order 10 to the minus, I don't remember, 39. Sorry, I had the Zoom page on the number. So if we had such a number for the charge of, if we have millicharged dark matter, which by the way, this is not constrained or anything, what we would obtain is a powerful jets comparable to the one observed in M87. Of course, we could have other configuration, as I told you, where EQ is just the charge of standard electron, and this K plus, for example, kappa plus, is much bigger than 1, and we need to understand dynamically how it behaves and why it could form, okay? Whether it could form and whether it could be reasonable to have such thing, okay? But okay, this is the main message, just to get a rough estimate. If we have maximally rotating or maximally rotating black hole, such as the one we observe in the center of M87, and some millicharged dark matter with this very tiny small charge, which is not constrained by anything, what we would observe is precisely, given the axial symmetric solution from before, we would observe precisely the jet power observed in M87, okay? So just as a comment, then I will stop and I will take questions because I think I want to discuss. You see, it seems like the flux here can become infinite in the limit of 0 charge. So I can have arbitrarily big fluxes. The answer to that, I mean, that's of course is not the case because there is a natural bound on the magnetic energy a black hole can sustain. Namely, the maximal magnetic field is bounded from above because you don't want a magnetic energy bigger than the whole. And this turns out in a bound on the maximal flux, which is square root of entropy, okay? So for M87, for example, such a bound would be 10 to the 47. This is just reading of the mass of the radius of this object. And in our estimate, to match the flux, we add the EQ, the charge to be 10 minus 39. So we have about 8 orders of magnitude within this maximal bound. So everything seems fine. I must also comment the following. Having charged millicharged dark matter, like this one here, induces a mass for the photon, and there are some bounds due to astrogalactic magnetic field. But okay, there is a very big region of space where these bounds are not affected. Our process, the mechanism can work in this region of space. Okay, so let me give you my outlook very briefly. So the first thing, these are things that needs to be done, and I'm planning to do. So the first question is whether we can have saturons with multiple vortex, like something like the pictures here, or maybe something like vortex anti-vortex with bigger winding number. This we would have to ask about their dynamics and understand how they interact and how they align with the rotation of black hole, for example, how they realize a rotation of black hole, and whether this can provide an understanding further correspondence with slowly rotating black holes. Okay, and the ideal place for this, maybe it's looking for saturated condensates, where there we have lattice configuration of vortices, and maybe we can understand better this issue. The other question is, of course, if we have a strong magnetic field, and for example, in the case of M87, we observed an accretion disk. We don't know if it's magnetized, but we observe it. How this is affected, how the emission is affected by the presence of magnetized accretion. This requires some numerical studies. Then, okay, if we have some vorticity, the question is what signature in binary mergers can stem from this. These objects are macroscopic, so they can back react on the dynamics. And okay, these are further questions. These are related to vorticity, it's more general. Namely, whether we can use saturons to better understand the late time evaporation of black holes. For example, we know that normally what is assumed is that black holes have a self-similar evaporation, namely that a black hole evaporates and turns always in a smaller black hole, keeping this self-similar construction. However, I mean, it's obvious that at most by page time, this can no longer be the case. It has to deviate from this thermal emission. And this is also suggested by this microscopic picture, because that would be the time of information retrieval of the internal information of the hole. And therefore, it will be interesting to understand how fluctuations and how the late time evaporation of these saturons can help us shed better insights on these questions. Okay, so I thank you for your time. I think it's 8:30. It's 30 past, half past. So I think it's okay to stop here. So thank you a lot.
Thanks a lot. Let's thank the speaker, Michael, again for the very nice talk.
Thank you.
All right, is there any questions from the audience?
What should be the mass of your millicharged particle so that it will be consistent with gravity as the weakest force constraint?
Yeah. So you see, I have this backup slide. So you see, what happens is that the moment I have a charged dark matter, what happens is that I induce a mass for the photon. Okay. And we know that the mass of the photon on a galactic scale is constrained by galaxy magnetic field, okay? So namely that the mass of the photon should be smaller than, this quantity. And if we focus, for example, to the case of 10 to the minus 39 charge, what we would need, you see, we would look at this equation, right? This EQ would be very small. Rho local, we pick a representative value, which could be the density of cold dark matter around the black hole. This could be, for example, 10⁴ eV4. But this is still, I mean, even taking higher value is still fine. For example, M gamma of order 10 minus 18 eV, that's within the bound. And if we assume that dark matter is also this value, everything would be fine. So this is the following, you see. So for simplicity in this example, I'm assuming that the induced mass of the photon is the same as the mass of the cold dark matter. This is a mass of 10 minus 18 eV. Actually, the mass of the photon is around 10 minus 14 eV, the bound that follows from here. Then what happens is that in order to realize this equality, we would need, with EQ equals 10 minus 39, we would need our local, which is given by this, which is kind of okay with what you observe around black holes. And this value of the mass, of course, you can tweak it. You can have lighter dark matter and different local. You can break this equality. You can have lighter dark matter. What we observe is that, for example, this mass would be close to this cold dark matter candidate would be close to fuzzy-like dark matter. We are not drawing any analogy with it or any requirement about it. We're just saying this is kind of similar to those scales, just to have a...
That's clear, thanks. I was just wondering if you compared it to this gravity as the weakest force conjecture, right? Because there are certain literature that claims that you cannot just arbitrarily have lowest couplings possible, right? So the photon exchange between these particles is weaker than gravity, right?
So,
but it's just it seems in violation, right? Is that
personally, I haven't thought. I haven't thought of this question. I don't know if it's really a violation. I would have to think about it.
Okay, thanks.
Sorry, it's okay.
Sorry, can I ask a very silly question? So
Sure.
if the photon mass is 10 to the minus 18 eV, is this really not completely ruled out? Because I just tried to estimate like what the fall off time scale would be for light. And it's pretty long, but it's not that long. It's a few parsecs. Did I just do it wrong? Or?
Yeah, so the point is that, okay, this is precisely, this bound on the mass of gamma is discussed by these people. And it heavily realized, so before that, what happened is that it was, historically, what happened is that they were putting a bound on the mass of the photon. And this mass was based on the assumption of a Procca-like mass term. But what it turns out is that this is and the bound was much stronger, okay? But what happens is that the microscopic origin for the mass of the photon plays an important role in the derivation of this bound from galactic magnetic field. And what happens is basically, this is related to the fact that basically if you have a galaxy magnetic field, the photon, what can happen is that vortex structure screening the magnetic field can form depending on the couplings of the theory, and therefore changing the phase. And what it turns out is that the mass of the photon turns out to be smaller than this value. And the numerical value you get from the galaxy is exactly 10 minus 14 eV. I know it's rather short. This bound is from 2007. I'm not sure. I understand your point that it's rather short, so perhaps it could be better. I don't know if I've tried to look for better bounds, and whether it improved or not. I couldn't, but okay. Maybe
Sorry, the PDG bound for the mass of the photon is also 10 to the minus 18 eV, but and it's also 2007, but it's from a different author, Ryotov, and but it's coming from, it looks like what they're saying, magnetohydrodynamics of the solar wind and extended out to Pluto. So completely different argument, but it's the same limit. It's 10 to the minus 18.
I have a very stupid question about this. I mean, that's I just checked again. I think that's a scale of order 10 light years in length. I mean, that's not very far. I mean, if really the photon mass was 1/10 light years, you would look and you wouldn't see most of the stars, right? The light would die before it got to us. So this doesn't seem right.
No, that's not right.
Why would you not see it? It would still get you.
That's not a lifetime of photon.
The photons have much.
It wouldn't travel. The photons wouldn't travel at the speed of light, right?
No,
but almost at the speed of light.
True. So what?
No, but look, they have energies of whatever their energies are. If they're EV energies, but their energy over their mass is, they're highly relativistic, right?
Yes.
I think that the point of Gia's paper, the old paper, was to show that you cannot just take galactic size and naively of magnetic fields and naively invert it as the strongest bound on the photon mass, because he and collaborators argued that if this mass is provided by the Higgs mechanism, there will be a breaking of that through the vortices, and this vortex
Exactly.
will support this galactic magnetic field. So that is fair. Yeah. So.
So
there are some stronger bounds, but there's I'm just looking. There's a bound from the galactic field,
right.
proto-galactic field.
I guess if you
just what I was saying,
if I may a second, if you just write what's called a Stuckelberg mass, right, the contact mass term without any supporting structure, then the stronger what's called the Parker bounds, I guess, so that would imply, right, or something similar to Parker bound, something from the largest scale magnetic fields, but if it's coming from the Higgs type mechanism, then the weaks is much weaker. Yeah. Sorry. Yeah, I spoke too much.
Yeah, from the galactic fields, then, well, at least what they're saying, because there's a paper by Edelberger from 07 as well, and they have the limit if it's a proto-galactic field, then it's 10 to the minus 26. And they say there's no limit really if it's taken as a Higgs particle from the galactic field.
That's exactly what I was saying, that the strongest limit comes from the assumption that it's precisely like a Proca-master, but the microscopic origin, as I don't know who told earlier, comes from that, like the microscopic origin of the mass of the photon matters for these bounds. And as it was correctly explained, the reason is that if the photon has an origin like a Higgs mechanism, then it would screen via vortices the magnetic field, and this would get in conflict with the values. By the way, just to a remark, in order for this, you see here, I just for simplicity took M gamma over the M dark matter. One could just take M dark matter to be heavier, and this would suppress the M gamma. You see here, I just for simplicity took a value close to the bound, which is 10 minus 18 AV. But I can break this equality. M gamma and M dark matter do not need to be equivalent. I could just take something that is much heavier for dark matter, and this would result in a much lighter photon mass. Okay, this is just to give an example of the parameter space, what up at the border, sort of. But then there is a huge window where things can work properly.
Okay, any more questions from the audience? All right, if not, let's thank the speaker again.
Thanks a lot.